Alright, so let's continue with our AVL trees, and hopefully in this part of the lecture we will look actually at practical implementation in C++. But so double rotation, let's look at the insertion basically, right? So find a spot for the value, which is basically binary search tree, right? And basically if you have imbalance, that's it, only single imbalance. So easy. So this is the easy case, right? We insert in what 3? Insert 3, which means so 3, 1, 2, 0, 0 is all good. So where do we insert 3? We insert here, right? Nothing do, right? We insert here and nothing happens, right? I mean, balance is preserved, right? Or is it? Easy insert. Change here 2, right? Here we'll have 1. Yeah.
Seems to be alright.
Yeah, this is easy. This is indeed. So hard insert, bad case 2. We have 3 already. Insert 33. So where are we going to put 33? Here, right? Right side here, right? So how will this be solved? Well,
There would occur a problem on the layer at 12 and 20.
yeah. So 30 will go here, right? No, see. We'll need to rotate up, right?
I think so, yeah.
Yeah. Let's see. Single rotation. Single rotation here. Okay, actually. Because the problem is here, of course. Yeah, problem is here, right? So 20, right? So what happens here? 15 is of course the new child, right? And so it inherits the children of 15 here, right? So that's the thing. So because that's where the problem is. The problem is not here. The problem is here. Because up to here, this is fine. The problem is here, 0 and 2, right? That's where the problem lies. Okay, makes sense. So again, the tricky part, of course, is that how do you attach these children, basically, right? So when 20 goes up, right, the right side stays same. Left side, basically, 17 attaches to this 15, right? This goes down, basically, right? You guys see it?
Yes.
So tricky, but of course after this rotation, so again the best part of AVL of course is after this single rotation you're done. Right? You're still good and you actually have this again, no more, the imbalance is no more than 1 basically, right? That's really good to know. Let's say the right side doesn't matter, but it's all off by 1. So this is one bad case. So another hard case. So now insert 18. First of all, where does it go? It goes here, right? Okay. It goes here, if I'm correct, right?
Yes.
Yeah. And now how do we fix it? We'll need to move up. Let's take a look. All right. Single rotation. This is bad, right? This doesn't look good, right? We didn't solve anything, right? This is would be the bad case, right? Basically, we are stuck, basically, right? Not stuck, but it's not what we want, right? So how do we fix it? Let's take a look. Where could we put? Instead, we move. The idea was to move.
So we will have to do the double rotation.
Yes.
The 17 would go where the 15 is.
Mm-hmm. Yeah.
And
yeah. Well, let's.
yeah, and then it would inherit 15 and 20,
Mm-hmm.
and 20 would inherit 18.
Mm-hmm. Let's take a look. Okay.
Oh no.
No. Wait, this is not done. This is not bad. This is still bad. Okay. So 17 goes here, right? Under 15, right? And this is okay. Now we can solve this, right? Now 15 will go up, right? Yeah.
Yes.
So single rotation, then the next one is easy, right? And then you move, yeah. Okay. See? So this is the first step, right? This is the tricky. So this is the hardest one again. Oh, they figured this out in 1962, right? Again, they must have been thinking about this hard. So second part is, but now we don't have to worry about it, right? This preserves the property. And this is the reason we actually can because it's double rotation again. People really don't want to write this code, basically, right? I mean, it looks okay visually, but you know, if you mess it wrong, of course, your whole tree is just basically broken, right?
I mean, you could do it in a single step.
Yeah.
In the first explanation image.
Yeah. 15, and of course. So this looks okay now. So this is okay. 2, 2, 1, 0, 0. You know, nothing. So looks pretty good, right? 1, 1, 2, 2 looks very well balanced actually, almost as good as you want, basically, right? You know, so you really can't go too much out of balance, basically, right? So, like I said, I like AVL, right? So this is the algorithm, right? So recursively or iteratively, right? So depends how you do it, right? Well, you end up using a stack, some sort of stack structure eventually, right? You insert node, unwind stack, correcting heights, right? So with the recursive solution, you sort of like you can correct, right? Basically, right? Or do a yeah. So second part in iterative solution, you need to keep track of these parent nodes, basically, right? You need some sort of, I don't know, put them in a stack or maybe some sort of hash map or something. Let's store them, right? Because you need to access them, right? And then you need unwind the stack, correcting the heights, right? If there's one imbalance, single rotate. If there's two, there's double rotate. But the thing, let's go back to this part here, this hard one. So here again, we are messing the double rotation, right? We messed around with what? 17, 20 here, right? And then we mess around with 17, 15, and 20, right? So 2 rotations, right? So only 3 elements involved, basically, right? So this is a C in regular C code, but it's also C++ code as well. But then let's go into, let's see, actually, let's write it first, and then we can check, right? Deletion, same thing, right? Just of course in reverse. So deletion single case, if balance is not changed, goodbye, right? But that's of course only for leaves, right? Pretty easy case. If we delete 15, right? How do you do this? So 17 can take over, because let's see how that works. Pretty easy case. And this is 2, 2, 1, 1, 0. Yeah, this is fine. Hard case. Let's look at this one. So we delete 12, right? It's a leaf, right? Deleted. Then we have a problem, right? We have a problem, and we have a single rotation. We fix the problem. However, we still need to check the other balance too, right? 2, 1 looks okay, right? So this is the hard case. Oh God, right? So this will be harder. So at the moment it's still an AVL tree, right? 1, 0, 2, 3, 2, 2, 0, 1, 0, 1. Yeah, it looks good, right? So we get rid of this. Immediately, what happens? We have nothing, right? And this is so this will need to fix this part here first, right? So we fix this part here, right? 2, 1, 0, right? But it's not finished, unfortunately, right? 3 rotates up, right? But suddenly 1 and 3 is still not finished. So what do you think is going to happen? Well, I have a theory. 17 will go up, right? 17 goes up, 10 will go left, and then 12 will attach to the 10, I believe, right? This rotation, 10, 17, 12, right? So 17 is going to be the new root, 10 is going to go down, and 12 will attach to the right side, and it preserves everything, this rotation. Let's see if I'm right. I have not seen these slides in a while, so let's see if I'm right. Right, so 17. We actually have a choice. It says double or single rotate. I think 17 will go up. I'm saying it. Maybe I'm wrong. Yeah, I am right in this case. Well, at least that's one of the solutions. But this is still okay. 1, 2. Is this okay here? 1, 2, 0, 2. Oh, yeah, it's fine. Truth, yeah, so it's fine. So this is fine, right? Or could we do this one? Let me see if I can. This is harder, right? 12, instead of doing 12, attaching 12, we attach only 11. Oh, 12 moves up. That's trickier. And then we attach 11 to the right side. I don't like this one. I think this is easier. This to me seems easier. So you have a choice, and that's unfortunately. So you have to look at the concrete calculations. There's two ways of maintaining the balance. I think I like this one better. What do you think? This one makes more sense, I think. Or not so. So we move 17 up. Of course, the whole idea is because whichever side is heaviest, I mean, I say more height, that's one is going to have the new root, right?
Yeah.
And the trick is to attach. See, if you move this to the root, this is free to be attached to the old root as the right side, and then everything just works. So now the problem I think with deletion is that in the worst case scenario it could have involved multiple levels, so multiple times, right? So it could be log n times, I believe. That's where this log n comes. Because right now it's been like just a single, do it once or twice, but no, theoretically, in like the worst case deletion scenario, it would take log n operations. Are you? Think about it. It's raining.
But in this case, it's only a single rotation.
Yeah, it's a single rotation, but that is propagation. We had to do it before, right? It's it's single rotation, but we had to do it before some other rotations before, right? So at each level. So yeah, this double. So deletion, recursive, stacking parent nodes, unwind stack, creating heights. So not so bad. So input n log n. We know that, right? A building is n log n. If it's sorted. Well, if it's sorted, we can actually beat it, by the way. Yeah. So that's another thing, of course, if you have sorted, which means it goes back to this one here is sorted, right? Obviously, right? Can we do? I think that's right. Might be the idea, so this actually been taught before, that you can actually do better insertion, right? Right. Build 3, divide and conquer, right? Start at half, and right. Of course, this involves knowing where the half is, but you can do binary search, right? And do recursive division, right? And then you will have how long will it take? Build the example, right? Turns out we have a recursive. See, you remember this guy here, right? From our formula, from our master formula, right? This is 1, right? So this means this part is going to probably dominate, right? And this is what? A and B, right? Right? This is A, this is B, right? So log A base of B is 1, of course, right? So by master formula, right? This is approximate, but we have the master formula, right? So we already know the answer here, right? It's going to be n, basically, right? So this means we can build a tree, sorted. If we have sorted some sort of sorted data, you can build a tree, AVL tree in O(n) time, on average, basically, right?
So technically, if we take any binary tree,
yeah,
and we just squeeze it into a
Yeah.
sorted array, then we
yeah, and of course, any binary tree, how can we get sorted? By using which traversal? Who remembers? I'm trying to figure which one. I think it was pre-order, I believe, right? Let's double check if I remember correctly. This is like a couple lectures back, right? I've forgotten everything, right? Pre-order, I believe. Let's see again. Let's look at our paint. Let's do our paint structure. Let's do our paint structure and let's figure out which one can we use. So this is a good point. Right. So I'm going to do a random binary search tree. Right, I'll do like 10. I don't know, 8, 12, 11, like, I don't know, 16, right? That's 10. And I don't know, 6. 6, and I don't know. This is an AVL tree technically, right? But okay, I'll add something like, I don't know, 2, right? So this is not an AVL tree anymore, right? So I can add maybe something, because here's the imbalance here, right? Imba, right? So what can we do? This is still not an imbalance, so I'll add like 4, right? Okay, so we know 2, 4, 6, 8, 10, 11, 12, 16. So I think it's pre-order, right? Pre-order, right? DFS, right? DFS, yeah, DFS. So we go, we don't visit, yeah, pre-order, or wait, or in order. Because pre-order we would check, or in order traversal, right?
Oh, yeah, you just search in order.
Yeah, it's in order traversal, of course, makes sense, right? So in order. Because we visit when we are here recursively, right?
So we would start with 2, 4.
Yes,
6, 8.
yes, it makes sense in order. So you would end up with 2, 4, 6, 8, 10. And then we have that. So we can convert any. The only question is now, the problem is, right? Here's the problem. To build this, how is this gonna be? If we want to build this list, what's the complexity of this building, this traversal?
Well, the presentation stated that it's all of n.
Yeah, but that's when we have the sorted list already, right? But the process of getting it from out of BST, right? We have n elements, and potentially. That's a good question. Or is would we guys get a linear approach? I don't see a linear approach because, well, I mean, if you have this, right? This is even easier, right? So, right? 1, 2, 3, 4, 5. How much time takes? Is it n or is it n log n? Because you have to go up down. DFS
Well,
should be linear.
according to ChatGPT, it is all of n.
It is ON.
Yes.
Okay, good. Okay, full. Again. Okay, good. So ON. All right. I'm not gonna prove it. Right. Prove it. It's exercise next left to you. Prove it. Luckily, I don't have to do it today. Prove it. Yeah. Okay. Right. Now. All right. All right. So. All right, we almost finished. Let's do a quickly see what a Copilot gives us as AVL3 implementation and see if it actually works. I don't know. This is going to be a challenge, right? To understand the code, right? First of all, I need to find where's my repository? I have too many AVL3. Where's my repository? Come on, I can't. Okay, let's get rid. Okay, this is done. Schedule is done. Too many tabs. Where's my GitHub? No. Oh, there. No, but this is the. This was that's that. Nope. Visualization. I guess I must have closed it. Maybe. Or maybe here. No. Let's do one more GitHub. Should be cookies, should be still active. All right. And see how well we do on our list structures. This is not something you should do without any assistance in the first run. I mean, maybe you could do it. This would be probably at least, you know, would take half a day to verify if this actually works correctly. So binary search we have AVL3. All right. Let's see while it loads up. All right. Okay, now it's good. Let's build then AVL3. Okay. From scratch, right? So import. What do we need? IO string maybe vector. Okay, that's good. Okay, why not? That's easy. It makes life easier, right? Algorithm. Okay. Q. Okay, it's getting a little stack. Okay, what else? Math. Okay, I don't know. It's getting too maybe a little too greedy. Right. All right. Let's do class node. Of course, node. We know how to do it. Right, int data left right, so that's easy. Okay, simple constructor, not a random one. So default constructor, right, height null pointer height is 1, right, crucial. AVL requires, right, so height again, yeah, but by default we have 1, right? Okay. No, that's our node, right? That's just for node. I would say structure node actually, right? Public, because, you know, well, okay, but that's good enough, all right? We have used.
But doesn't the AVL also require to know to have the parent pointer?
Yeah, that would be actually good. Well, it doesn't require, right? But it'd be nicer, right? Could we do this? Actually, I think it'd be much easier, right? I think it'd be much. Well, it doesn't cost that we need to update this, right? Of course, then, right? But it's easier, I think. We could, I think, survive. I think the original literature didn't use it, but let's see what happens. We can update afterwards, right? Because right now we'll do recursively, right? It's going to complicate things when we do rotation, because going up is going to be pain, right? I think let's do this. Let's add a parent. This parent. Yes, I think so. Let's.
You should also reference it at the.
Yeah, we don't have it. Right. Yeah. Helpful to make navigating on navigate. Yeah. Right, because that makes deletion. It'll save us a lot of pain on the on deletion, right? Because we'll keep navigating, right? Good idea. Okay. Now class AVL. Let's see what's happening. So what we have, we want public, right? Node root AVL, this root null pointer, right? That's easy, right? That's easy one. Yeah, there's public code. It's from some public repository. So get height, right? If node null pointer returns 0, otherwise you have not, it's just a getter. Okay, that's boring. Get balance. Okay, so this is where the fun starts. So how do we get balance? We check left and right recursively, right? Well, get height, right? From okay, no. So this actually not even recursively. We just do it directly, right? Okay, so that's fine. But now right rotate. Okay, so this one, this is what's supposed to be doing the rotation. Right rotate, right single, right? And we need to also update the heights. Do we also have parents? New root height. Let's see. New root right. I'm a little bit suspicious that that does not have the parent. Unfortunately, I have a feeling, right? I think this is not going to work. Well, it might work, but deletion won't work, right? Because we don't have the parent information updated. So this will need to be updated, right? I don't see parent being added here, right? Let's take a look. Well, first of all, we'll check it works. Node insertion. Insert, right? This is recursively, right? Yeah, I don't see parent anywhere, unfortunately. Okay, it's still if on right rotate, if balance, right, we check the balance, okay, and we still need to finish this. So we have insertion, we have deletion, and that's it, search, right? We need also search, of course, right? What's missing still?
The braces.
Braces from the
Yeah,
class.
from the class.
Okay. Okay.
And oh, this was from the function, and then another.
Yeah, I
brace from the
think,
class.
yeah. Don't we need also the class?
Yeah, right.
Yeah, okay, now it's okay, but the question is no. So we left return, return, return. I'm a little suspicious. It's supposed is it all case covered, right? Have we covered all cases? Have we covered? Right, you guys finishing, right?
Oh, I have to go.
Yeah. All right, so we're gonna finish in about a couple minutes, right? So I might, well, I'll give you this extra challenge to check if this code is correct. Add parent pointers, right? I think you could do it. I know you guys could do it, right? So I would like to. One thing I would like to do. What do we have? Let's look at the outline. What do we have? We have node. Okay, node is okay. Root, get height, get balance, rotates is fine. Insert is okay. We need what? We just have insertion. We need deletion, of course, right? Now delete. Now delete. You have to remember this is still right. So node pointer, delete node, delete node. Yeah, get balance, return right rotate. So we have these movements. So a lot of code, right? So and it still doesn't have the parent in order. Yeah, so this is good. In order traversal, right? Just basic, in order, right? Print traversal functions will print in order, right? Makes sense, right? So this is on order. We talked about this, right? Also, find value. Fine, we want this one, right? So recursively again, right? What else do we want? So is it existence check, right? Or null pointer, right? Returns find value, return null pointer if not found. Okay, I think we are ready. Let's see this check. Let's see this compiles. Now let's check. Now, right? Main, of course, right? Int main. Okay, we have insert some values. 3 in order. Delete node 30. 3 in order. Delete 40. Delete. We don't delete everything. Okay. Well, it's going a little crazy. Let's compile. Let's not. Okay. Okay. Let's compile this. And do you think it's going to work on the first try? I have my doubts, but maybe it will work. The thing what I don't like is that it doesn't have. Come on, what's happening here? Oh, because yeah, AVL. Oops. Warning control reaches end of non-void function. Let's look at our insert. This is one of the one. So let's look at 114. Where's 114? This is one of the things which is suspicious. Right. Yeah, we need to return something. Return node. Right. Insert new node. Right. If node no pointer, easy. Yeah, we need to have the case. Get balance, return right rotate, left rotate. This is so 114. We are, but the problem is basically we are not. What do we return? Return. Yeah, is that gonna work? Let's see, node. I'm not sure. This is kind of suspicious. it compiled, but this is a little suspicious. This is not. I'm not check if it's correct. Check correctness. If this is ever reached, because what's happening is this, right? The compiler, it checks if you're doing if, right? There's no else. So I have a feeling this is always, we'll have all three cases, right? We are recording all the cases, balance, right? Right. Otherwise, we don't really need to do this. The light rotate returns a node, right? Yeah. Okay. Yeah. Okay. Let's see this runs. I don't know. This thing's gonna run. I don't know. It's gonna break. No, it worked on the first try. Okay, it's good. We can go home and eat. All right. So it works, but okay. What I will add to do, which does nothing. I didn't see anything to do. Add support for parent pointers, right? In next implementation. Okay, so that's something to do next time. All right. I will add this. We will 3 example again, and also to do more tests would also be helpful, right? And it's sort of like it looks okay. First smell test passed, right? But maybe this is just a slight illusion. But what would we need to check, right? We didn't check all the cases. Just this deletion works, insertion works, right? It looks okay, yeah. But maybe we need some other. We didn't check all rotations. I'm pretty sure. Okay. So what did we learn today? AVL3s. Obviously use them if you have them. Don't implement them from scratch. All right. They will have generally better performance for lookups, right? That's a big thing, right? They are more hard to implement, but better balance, right? So databases use them also, right? Anywhere you have read-heavy operations, AVL3 is actually something to consider. All right. So thank you, everyone. Do you have access to the quizzes question before we go?
For today?
Yeah.
For today, yes.
Okay, good. All right. And do we have? I think we have one more. Do we have one more? I don't have any more assignments, but I thought I was going to give you one more, maybe. Yeah, I'll give you one more assignment.
It's alright.
It's all right?
Yeah.
Yeah. Okay. We'll talk about this, right? Maybe it's enough. Maybe it's enough, right? We already have enough assignments. All right, so I'll see you guys on Thursday. Any questions for today's topic? Able to follow? Yeah, more or less. Obviously, to go deeper, you have to see and play around with the trees itself.